We're going to begin this course with a rather intuitive discussion of the idea of continuity. In math, the term continuous to a great extent is the same meaning as we use it in everyday life. Take that to mean that there's no gap in the graph at that point. So if you were to draw a graph of something that was continuous at a point C, what you would say is that it has to satisfy two conditions. The graph has to be unbroken at C, there can't be any break in it, and it can't have any type of hole, jump, or gaps. In other words, point 2 is really just a description of what unbroken means. It can't be broken at C, and those breaks can be caused by holes or jumps or gaps at C. So intuitively, we would say that a graph is continuous if we can sketch it over an interval without lifting the pen in the process of doing that. We would say it's continuous over that interval. So I've just sketched out something here with arrows on each end, which means it continues in both directions indefinitely. There are no breaks in the graph at all, so the graph could be said to be continuous on the interval from minus infinity to infinity. In other words, the set of real numbers. Any value, and this is the intuitive part, any value where we must lift the pen is a point of discontinuity. So if you're graphing and you have to lift your pen or pencil from the paper to complete the graph, you've found a point of discontinuity. Some simple examples, and you've done things like this in previous algebra courses. There's a discontinuity at 3 because there's a hole in the graph. There's just no value at x equals 3. You have to skip it. There's a hole there. There's no value at 7 because that's the vertical asymptote. To the left of 7, the graph runs down the vertical asymptote. To the right of 7, the graph runs up the vertical asymptote. There is no value at 7. So graphically speaking, you can sort of look at a graph and see these holes or discontinuities caused by vertical asymptotes, and those places are just blare out at you if you have the graph. So this graph has a discontinuity at 3 and it has a discontinuity at 7. Those two discontinuities are different from each other, and we'll talk about how. Once you accept the fact that the graph does have discontinuities, you can look at the intervals around those discontinuities and say that you still have continuity in the intervals around those values of discontinuity. In other words, if you cut the thread at 2 places, you have 3 pieces of thread, and each piece of thread in its own right is continuous. There's no more breaks within each piece. So overall, the function is made up of 3 pieces that aren't connected to each other, so you have 2 discontinuities that break the graph into 3 pieces. But each individual piece itself is continuous on its domain. So I could say that this graph, although it has 2 discontinuities, is discontinuous at 3, but to the left of 3 is continuous. So from minus infinity until it gets up to 3, there's continuity for that piece. And then between 3 and 7, there's continuity. You can draw that segment of the graph without lifting your pen from the paper. And then again, once you pass 7, from 7 to positive infinity, you have continuity. So the graph, as originally presented, has 2 discontinuities, 3 and 7. Those 2 discontinuities split the graph into 3 segments. Each individual segment on its domain, on its own domain, is continuous. So be thinking that over. It's a simple idea, but you might have to think about it a few times to get it down the way you need to, because it's a very simple idea once you understand what they're saying there. There are 2 results that are going to help us through this discussion of continuity that are very important, and they have to do with the continuity of polynomial and rational functions. The first of those deals with polynomial functions, and it says that a polynomial function is continuous at every real number. So game over if you're asked ask about continuity of a polynomial function. You can just automatically say that it's all real numbers, and the way you say that with interval notation will be minus infinity to infinity. The other possibility that we'll talk about explicitly is with rational functions. If you have a rational function, in that previous graph that I drew with the hole and the vertical asymptote was an example, the rational function is continuous around its discontinuities. In other words, at every number in its domain, because those discontinuities are not in the domain of the rational function because they cause division by zero. So the second one basically says, yes, a rational function can have discontinuities, but if you look at the segments around the discontinuities, those segments themselves are continuous on their domains. Let's look at a few examples. All the first few examples are going to be polynomial functions. F of x equals x squared minus 2x plus 3 is a polynomial. Remember, a polynomial is just numbers times x to positive powers strung together with pluses and minuses, and they can have a constant on the end. Those are polynomials. Game over when you do a polynomial. If you see a polynomial, you can automatically say it's going to be continuous for every real number, and you say that in interval notation by writing minus infinity to infinity with parentheses. F of x equals x cubed minus x, same thing. That's a polynomial. There's a polynomial. Game over. It's continuous from minus infinity to infinity. F of x equals x to the fourth minus 2x squared plus 1. Again, that's a polynomial. Game over. It's continuous from minus infinity to infinity. So if you can ever identify the function as being polynomial, you've got the answer. It's always going to be minus infinity to infinity, unless the domain is artificially restricted down from that, and we will see an example of that later on. But in general, unless there is some overarching restriction, it will be minus infinity to infinity. You don't have to graph these things to see what I'm talking about, even mentally, if you just think of a polynomial function with no gaps. But if you actually see the graphs, you can see, yes, they are continuous. There's no value that's undefined, or there are no vertical asymptotes involved. So even though you don't have to graph them to see that they're continuous on the entire real number line, if you do see the graphs, it sort of confirms your intuition. All three of those functions are continuous from minus infinity to infinity. Now remember, a polynomial function is continuous everywhere. There will never be a hole or a jump or any kind of gap for polynomial functions. But if you come to rational functions, on the other hand, that's not always the case. A rational function is a ratio of two polynomials. In other words, one polynomial divided by the other polynomial. And those can have values where the function's not defined. So a rational function is continuous on any segments around any discontinuities you find. And there doesn't have to be a discontinuity just because it's a rational function. But you do have to skip any discontinuities when you're listing the intervals where the function is continuous. And you'll see that in some particular examples. A simple way of saying that is that a rational function is continuous at every number in its domain. You don't have to say in the domain of a polynomial. You could, but a rational function often has some discontinuities whereas a polynomial function never has any. Look at these examples. Discuss the continuity of these functions. Well, now this is not a polynomial anymore. This is a simple rational function. In fact, this is the simplest rational function, just 1 over x. Going back to our conditions for continuity of a polynomial and rational function, this is a rational function, so we know that the rational function is going to be continuous at every number in its domain. So we have to figure out what the domain is, and when you're dividing by x, it's obvious that x can't be 0 because you can't divide by 0. So 0 is not in the domain of the function, and that tells you that you have to leave it out when you're talking about continuity. I would think of it in terms of a number line, and you think of 0 as being a value on the number line. You've got to stay away from 0. So a polynomial function is continuous everywhere, but a rational function can have a discontinuity, and it does in fact have a discontinuity here at 0. So you have to skip 0. So you can go from minus infinity up to 0. That's why you need a parenthesis. You go up to 0 but not include it. And then you can go past 0 to the right of 0 and go from 0 to infinity, and by using parentheses you're essentially skipping 0. So this polynomial function over polynomial function, which is a rational function, is continuous on its domain, but 0 is not in the domain. So you have to say, well, it's continuous from minus infinity to 0 and 0 to infinity, but you're skipping 0 itself. So the function is continuous on its domain, which is minus infinity to 0 and 0 to infinity. And notice that by using parentheses, you're actually skipping 0. because 0 is not in the domain. You cannot divide by 0. The more you play around with this, the easier this is to see. As with all these others, you don't have to have a graph to understand what's happening, but if you do see the graph, you can see that that value at 0 is a vertical asymptote, and you definitely have to pick up your pen to draw the left half and then go to the right half, so there's a discontinuity at 0. But as long as you stay to the left of 0, you don't have to lift your pen to draw just the left half. And as long as you stay to the right of 0, you don't have to lift your pen to draw the right half. So each piece of the function is continuous on its domain. The entire overall function, you have to leave out 0. How about this one? F of x equals x squared minus 1 over x minus 1. Again, the same conditions apply. This is a rational function, so you know that the rational function will be continuous at every number in its domain. But what is the domain? Before, you couldn't divide by 0 because if you put a 0 in for x, you got division by 0. Here, 1 is the problem. You can't divide by 0. Plugging 1 in for x is what causes you to divide by 0. So this time, you're leaving 1 out of the domain. Picturing it on a number line, you're doing the same thing that you did with the other one, except instead of skipping 0, you're skipping 1. So if you go to the left of 1, from minus infinity to 1, with a parenthesis, you're skipping 1, it's continuous there. And then if you go to the other side of 1, from 1 to infinity, again with parentheses, you're skipping 1 itself. The function is continuous on those two intervals. The domain is minus infinity to 1 union 1 to infinity. This point is not needed to answer this question, but it will relate to something we're going to do shortly. So I want to take this example just a slight bit further. If you take that numerator x squared minus 1 and realize that that's a difference of two squares, you can factor that as x plus 1 times x minus 1. And once you do that, you see that the x minus 1 in the numerator will cancel with the x minus 1 in the denominator. So as long as you don't let x be exactly 1, the original rational function is equivalent to that line y equal 1 plus x, or x plus 1. And again, that is just a straight line with slope 1 and y-intercept 1. Nevertheless, there is a discontinuity at 1 because you cannot divide by 0, and plugging a 1 in here would cause division by 0. So what we say, if a discontinuity can be removed by just a simple factor cancel, it's still a discontinuity, but we call it removable. And I'll show you another way of thinking about it when we see the graph. On the graph, you're having to leave out the value at x equal 1. If you plug back into here and you let x equal 1, you see that y is equal to 2. So it's the point 1 comma 2. So that's why we have to leave it out. There's a hole. And that's another way of thinking about a removable discontinuity. A removable discontinuity graphically is represented by just a hole in the graph. And the idea is it can be removed by filling in the hole. So if I just did that, it would not be a discontinuity anymore. So in that sense, it's a removable discontinuity. The more you play with these ideas, the more they make sense. How about this? F of x equals 1 over the quantity x squared plus 1. Now that's a rational function, and we're used to seeing those have discontinuities, but this is not the case here. It is a polynomial, so it is continuous on its domain, but this domain doesn't have any discontinuities because there's nothing you can plug in for x and get a 0, and you can, if you think about it in a minute, you'll see why. You're squaring a number and then adding 1 to it. Can you think of a real number you can square, add 1 to it, and get 0? Well, of course not, because when you square a number, it's either going to be 0 or positive. If you square 0, you get 0. If you square 1, you get positive. If you square negative 1, you get a positive 1. If you square negative 50, you get a positive 2500. You can't square any real number and get a negative, so when you add 1 to it, it's certainly going to be positive. So there are simply no values that make that domain anything less than minus infinity to infinity. In other words, there's no value of x that makes the denominator 0. So thinking about it like this is, it just fills up the whole number line. There's no value that causes a discontinuity. So the function is continuous on the interval from minus infinity to infinity. So it is possible for a rational function to not have a discontinuity. You just have to check it out. Again, you don't need the graph to do the problem, but if you did have the graph, you would see there are no holes, no gaps, no vertical asymptotes, nothing like that. It's continuous from minus infinity to infinity. We can now talk about a little bit more technical, the idea of a continuity or discontinuity over an interval. And the interval could be minus infinity to infinity, but it could be a smaller interval as well. We've already talked about those discontinuities and that there are two types. The removable type we've already discussed a little bit. The non-removable we'll get to shortly. But again, the removable type, looking at the graph, you would see a hole in the graph. Looking at the algebraic expression of the function, you would see something where a factor could cancel out and get rid of the discontinuity. That's the removable type. And we just did that in the example a minute ago, and we found out, remember, that when we factored x squared minus 1, we factored out the x minus 1. It canceled with the x minus 1 in the denominator, and we ended up with a straight line with a hole in it at x equal 1. And when you plug 1 into that equation of the line, if you plug 1 in here, you end up with 2. So that's why that hole is at the point 1, 2. The hole is at 1, 2 because when you plug 1 into this function, you get 2 for y. So that's a hole. What about the non-removable type? The prototypical example of a non-removable discontinuity is a vertical asymptote, and you've done those before, the functions that have vertical asymptotes. F of x equal 1 over x is a perfect example of that. You can see that there's a vertical asymptote at x equal to 0, and you cannot fill in a hole and get rid of that discontinuity. We call that a non-removable discontinuity. In this case, the discontinuity is at the vertical asymptote, which is x equals 0. Let's just do some examples. This problem says to sketch the graph of the function f of x is equal to a function defined by a rule. It's x squared minus 2 as long as x is less than or equal to 0. It's 4x plus 2 when x is bigger than 0. Now if you think about it, they did the graph for us. We just have to use a process of elimination to figure out what it can't be. Now what I would probably say is that it's really pretty simple because those graphs of each of those pieces are simple polynomial functions. X squared minus 2 is a parabola, and 4x plus 2 is a straight line. Well, when you say something's less than or equal to 0, that means it's going to the left of 0, and including 0, that's to the left. So what it's saying is, if you look to the left of 0, you're supposed to see a parabola. But if you look at the graphs, those four graphs, the two in the middle, if you look on the left side, this is the left side, you don't have a parabola on the left side. If you look on the left side over here, you don't have a parabola. So just by noticing that one thing, you can already cut your choices from 4 to 2. So now it's just a matter of, is the answer A or is the answer D? The first one or the last one? They're both straight lines. If you look at the second condition, you've got a 4x plus 2. It's a graph with a slope of 4, which means it's going up, so you could probably tell already that it's the fourth one. But you could also just plug in a value. So you could say, okay, I don't want to think about it too much. What would happen if I plugged 1 in for x? Well, if you went up here and plugged 1 in for x, right here, you would get 4 times 1 plus 2 would get 6. Well, which one of these graphs is it? 1, 6 is up here. So it's obviously not that one. 1, 6 is about right there, so it looks like that's the right one. So what I'm getting at is a lot of these graphs, since they're already done for you, you really don't have to graph them per se. You can just eliminate all but one possibility, and that what's left has to be the right answer. How about this one? Another function defined by a rule. But it's completely contained between minus 1 and 3. Nothing goes less than minus 1, nothing goes bigger than 3. They're both polynomials though. 5 minus x is a polynomial function. X squared minus 1 is a polynomial function. So we know from our earlier discussion that polynomial functions are continuous everywhere. So 5 minus x is continuous everywhere. X squared minus 1 is continuous everywhere. The only place there could be a discontinuity then is where the two pieces connect to each other, and that's at x equal 2. So when you see problems like this, all you really have to do, if you notice that the rule has pieces that are all polynomials, all you have to do is look at the places where the two rules connect to each other. In this case, it's at x equal 2. And the graph doesn't go from minus infinity to infinity, though, too. It just goes from minus 1 to 3. So you plug 2 into the top piece. The top piece is 5 minus x. When you plug 2 into that, you get 3. Then you go up here and plug 2 into the bottom piece. When you do that, you get 4 minus 1 is 3. And they're equal to each other. So that means the two pieces of the graphs come together. If those two values are different from each other, there's a gap and there's a discontinuity, in this case at x equal 2. But if the pieces come together and have the same y values, that means that there is no gap, there is no hole, the graphs touch, and there is no point of discontinuity. So the bottom line here is that this function g is continuous on its entire domain, and had they not restricted it to between minus 1 and 3 here, it would be minus infinity to infinity. But because they restricted it to being between minus 1 and 3, you have to stop it. You can't go any further to the left than minus 1. You can't go any further to the right than 3. But between minus 1 and 3, there is no gap. And the reason you know there's no gap is because you get the same y values when you plug in the place where the rule changes. Again, you don't need the graph to see this, but if you did take the time to graph it, you'd see there is no hole or gap. Okay, let's look at this example. Find the constant a such that the function is continuous on the entire real number line. So this time, there's some constant value a which is undetermined, and we want to figure out what a has to be in order for the function to be continuous. And if you think back to the previous example, the thing that made it continuous, and again, both of these are polynomial, both rules are polynomial rules. The thing that you could use to make sure it's continuous is for the two pieces to come together, and you find that by noting that the place where the rule changes, which in this case is at 8, if the y values are the same at 8 for both pieces, there is no gap, there is no hole. So all we have to do is plug 8 into the top rule. If you plug 8 in here, you get 8 cubed, that's 8 times 8 times 8 is 512. Then you plug 8 into the bottom rule. Remember that a is sitting there, so you've got a times 8 squared. Well, 8 squared is 64. That's 64a. And remember, in order for there to be continuity, when you plug in the two values, they have to be equal. So the condition is 512 has to be equal to 64a. Or saying it a little differently, 64a has to be equal to 512. If you divide both sides by 64, you'll see that a is equal to 8. So in order for this original function to be continuous over the entire real number line, a would have to be the number 8. If a were anything but 8, there's going to be a gap, and that will not be a continuous function over the entire real number line. How about this one? You've got a rational function, but the denominator is already factored. At this point, we have the graph as well, but you really don't need it. You can see either from the graph or from the original function that if you're looking for discontinuities, all you got to do is to find out where, if you're looking at the graph, it's where you have to pick up your pen to keep drawing. If you're looking at the function, it's what causes division by 0. If you're looking at the graph, you can see that you're at minus 5 and 5. If you look at the function itself, you can see that if you plug a minus 5 in here, you get a 0. If you plug a 5 in here, you get 0. So either way you look at it, the discontinuities are at minus 5 and 5. And as we talked about earlier, a rational function is continuous on its domain, but you have to figure out, once you know there's discontinuities, as long as you stay to the left of minus 5, that piece can be drawn without lifting your pencil from the paper, as long as you stay to the left of minus 5. So from minus infinity to minus 5, you can see you can draw. I didn't exactly overlap because it was so close to the asymptotes, but you can see that you can draw that entire left segment without lifting your pen from the paper. Notice I'm using a union symbol. Technically, when you're writing a domain, you'd put union. WebAssign is not very particular. If you put a comma there, WebAssign's fine with that too. So one of the things you'll learn in this course is you need to play around with WebAssign and see what you can get away with. If it'll let you do a comma and you'd rather do a comma, do a comma. Continuing, there's a piece between -5 and 5. And then finally, there's a piece between 5 and infinity. And as I said, WebAssign is not too particular. If you want to put a comma instead of a union symbol, WebAssign is cool with that.